All right, guys, let's start vodcast 11.1. This is going to be our last unit for the year, so hopefully everyone's pretty excited about that. We're going to talk a little bit about acids and bases, which very often is the stuff that students really want to know about chemistry. And the first thing before we even jump into all the notes and that stuff is don't think of acids like you see them in the movie. Acids don't work in the way that an alien has acid for blood and it hits you and immediately a person half their skin dissolves off. Acids don't usually work that quick. It takes about 9 or so hours to actually completely eat through like a chicken leg or something like that. So just keep in mind to sort of throw your movie conventions out the window when you're thinking about these. So if that's not what acids are, then what are they? Well, acids are first sort of defined by this guy named Arrhenius. Now, they had called stuff acids for a long time before this. This is Arrhenius right here. He's a Swedish chemist, and he's the guy that sort of does big work into ionic compounds as a whole. And in his course of figuring out ionic compounds, he also defined what an acid is. So under the Arrhenius system, it works like this. Okay, acids are things that produce H+. Okay, which in an H+, we should recognize as that is a hydrogen ion. Okay, now you may see this occasionally written in a different way. H+ essentially means the same thing as H3O+. Okay, and we would call this, okay, just like we would have called it all year, this is a hydrogen ion. Okay, and H3O+ is what we call a hydronium ion. Now, for all of our calculations and stuff, we're going to treat them the same way. How we get to H3O+ is that we take an H+ and add it to a water molecule. Okay, and that gives us H3O+. And all the things that we're going to be doing are in aqueous solution. So all of your H+'s basically get joined together within water to make an H3O+, which is called a hydronium ion. The reason that I sort of go through that is because you can see it in either way on tests and EOCs. It kind of depends on your teacher. I like to keep it simple and talk about H+ ions, but on the EOC you may see it occasionally written as a hydronium ion. You kind of have to know what both are. So that's what acids are according to Arrhenius. They are things that produce H+. Now, according to Arrhenius, bases, and we'll talk about bases here in a second, bases produce hydroxide ions. Okay, so anything that makes OH negative ions would be a base. So sort of a good example of that would be something like magnesium hydroxide. Okay, when that breaks down in water, it forms Mg2+, okay, plus 2 hydroxide ions. Okay, that makes it a base. If it makes OH minus, that makes it a base. On the other hand, if we went back up here to like acids, if we had HCl, when HCl goes into water and breaks up, we get H plus Cl minus. So the fact that it makes H plus makes it an acid. Okay, so real quick, some characteristics of acids. First off, acids have a sour taste. And you're like, oh my gosh, why in the world would I possibly eat an acid? Well, I mean, acids are in all kinds of food, but the tang that you get from like citrus, from like orange juice or lemon juice, or that little bit of bite that's in tomato sauce, that's because of the acid. Vinegar, obviously another acid that we would have a lot in food, and so it has that distinctly sour taste to it. It just gives it that little bit of bite that sort of causes you to pucker up a little bit. That is basically indicative of an acid. A couple other quick characteristics. Acids are going to change the color of acid-base indicators. Now, we're not going to talk a whole lot about this, but you probably did some of this in middle school where like you put drops of something into an acid or base and it changed colors, or maybe used a piece of litmus paper and dipped it in and it changed its colors. That litmus paper is a form of indicator, and we use indicators essentially for what they sound like. We use them to indicate whether something is an acid or a base. So they're going to change its color. And then the third thing is acids will react with metals to release hydrogen. Now this, we could sort of go back real quick and talk about single replacement reactions, but that's essentially what's going on. If you've got an acid so like hydrochloric acid, and you add to it an active metal like, say, magnesium, look on the activity series, magnesium is more active than hydrogen, so it takes its place. Okay, this is a single replacement reaction. And then what's given off is hydrogen gas. And we'll see an example of that here in just a second. A couple other quick characteristics of acids. Acids are going to react with bases. They're going to produce water and a salt. Now that seems confusing. We tend to think of salt as sodium chloride, and that can happen. But salt is a generic term for any ionic compound. Okay, it doesn't necessarily have to be sodium chloride. It could be calcium chloride or magnesium hydroxide. Or, well, magnesium hydroxide wouldn't be a salt, it would be a base. But anything that is not an acid or a base that's an ionic compound is what we call a salt. And then acids, most of the time, if they're aqueous, and that really should, let's change that a little bit. Let's make this aqueous acids, conduct electricity. So you can run a current through them. In fact, this is how batteries work. All batteries, whether they're dry cell or wet cell, basically have a combination of acids and bases in them, and that's what allows for the flow of electrons. So like your car battery has sulfuric acid in it, a couple of lead plates, or actually bunches of lead plates in it, and the acid is what's going to help to conduct the electricity in it. Okay, so those are characteristics of acids. Remember that what acids are things that are going to produce H plus ions. I want to real briefly jump back to something that we covered in vodcast 7.2, which is naming acids. I'm going to run through these pretty quick, so if this doesn't seem familiar, you need to go back and watch the end of vodcast 7.2. But here's the way it works. If it is a binary acid, meaning that there are only two things in it, okay, hydrogen and then whatever else it is, then we name the anion, that would be the F, so fluorine. Okay, remember that what we're actually going to do then is knock the end of it off, replace it with an IC, and since it's a binary acid, we write a hydro in front of it, and that becomes hydrofluoric acid. Okay? For everything else, if it's got an oxygen in it, basically that means there's a polyatomic. So you have to name your polyatomics, and then you name the acid from there. So like, in this case, my polyatomic is chlorate. Okay, and remember what we do there is that we're going to come through and if it ends in ATE, we're going to knock that end off and we're going to add an IC, but no hydro in front of it if it's a polyatomic. So it just becomes chloric acid. Okay, and then down here for the last one, if we wrote out that ion name, that is hypochlorite. Okay. Remember, if it ends in ITE, then we erase the ITE, and it gets replaced with an OUS, so that becomes hypochlorous acid. Okay? Again, go back to 7.2 if you don't remember all that. Okay, let's talk a little bit about bases. Remember that sort of a characteristic of what a base is something that produces hydroxide ions. But what do bases look like? Like, how could you identify something as a base if you didn't know what the chemical formula was and all that stuff? So how can we identify it? Well, first off, bases taste bitter. Acids taste sour and kind of pleasant, but bases taste, to be honest, pretty gross. And the best way that I can sort of describe this to you is that aspirin has a real bitter taste to it, even though technically aspirin is an acid. But it has a real bitter taste to it. Another thing that really tastes really super bitter like this is a chemical called quinine. If you ever had tonic water, it tastes that way. But it's really like sharp and unpleasant. Acids kind of taste good. I mean, they're kind of sour, but they taste good. But bases taste really bitter and nasty. So that's a good indicator there. Another indicator, bases are going to feel slippery. So if you got a base on your fingers, you sort of rub your fingers together, it would feel like you had soap in your hand. And actually, what's kind of funny is that if you have a base on your fingers and you rub it together, you do have a soap on your hand because bases react with fats and oils to form soap. That's how we make soap, is by reacting a base of some kind with oils or fats or something like that. And so when that slippery feeling that you get on your fingers is the base actually taking some of the oils of your fingers and turning it basically into a soap. Okay? Bases are going to change indicators just like acids. Okay, so in these ways they're similar. They're also going to react with acids to produce salts and water. Okay? And aqueous solutions of bases conduct electricity. So if you look at these things that we've got up here, the last three things are all in common with acids. Okay, the acids and bases both have those things. The top two things are different. That's sort of what's going to differentiate a base from an acid for us. Okay, so real quick, let's run through here, and I want to be able to identify things as an acid or a base, and then to name them if possible. So here's the way it works. If something starts with hydrogen, you can be pretty sure that it is an acid. Okay? Now, remember, we talked about this earlier in the year. We did naming. Water, obviously, is not an acid. It's H2O, although it can be an acid. Hydrogen peroxide starts with H, but those are kind of exceptions. Just about everything else that starts with H, probably going to be an acid. So let's name this then. This is a binary acid, right? And so that would be chlorine. And we know that we're going to change the ending of it to IC. And since it's a binary, just two things in it, we're going to put a hydro in front of it. And that becomes hydrochloric acid, which is obviously one that we use a lot. Okay. Look down here at the bottom. What is our polyatomic? Okay, it is acetate. So it ends in ATE, so I want to get rid of the ATE and add an IC on the end of it. So that becomes acetic acid. That's the stuff that's in vinegar. Okay, so those are pretty simple. Those are the acids. So how do I identify when things are base? Well, if it has hydroxide in it, bam, you immediately know that it is a base. Bases get named a little differently. You don't have to write base at the end of them like you write acid at the end of acids. You just name them according to normal ionic compound naming rules. So sodium hydroxide, right? We've used that one a few times. Jump down here to this one, calcium hydroxide. Remember, in these two cases, I didn't need to put any parentheses with charge or anything because sodium always has a +1, calcium always has a +2. This one, so what is this? It doesn't start with a hydrogen. I don't have any hydroxide in it. We know the name of this, right? It's ammonia. That's one of those kind of three things that we just had to know. Ammonia is a base, and we don't really have time to get into all the reasons why it's a base. But just real briefly, this is why it's a base, because it will absorb a hydrogen. So acids produce hydrogens, and under a different system called the Bronsted-Lowry system, bases are not things that produce hydroxide, but things that absorb hydrogens. That obviously turns that into an ammonium ion. Okay, so how do you identify them? In general, if it has hydroxides, okay, hydroxides make it a base. Starting with an H probably is going to make it an acid. All right, relatively simple.